In the vast universe of organic chemistry, amines are like the social butterflies of the molecular world, constantly interacting and forming new connections. They are derived from the humble ammonia molecule, NH3, but with a fascinating twist that makes them incredibly versatile. One or more of ammonia's hydrogen atoms get replaced in a process that transforms its chemical nature. In their place come alkyl or aryl groups, ready to mingle and form new, exciting compounds with unique characteristics. This substitution gives amines their unique properties and makes them essential building blocks in various natural and synthetic materials. Amines are everywhere, playing crucial roles in countless applications. They're in the DNA that makes us unique, forming the very essence of our genetic code. They're in the medicines that keep us healthy, acting as key components in many pharmaceutical drugs. And they're even in the dyes that color our clothes, giving us the vibrant hues we see every day. Understanding amines is like unlocking a secret code to a vast library of chemical possibilities, each more intriguing than the last. Imagine amines as tiny, energetic molecules, constantly interacting with their surroundings, always on the move. Their nitrogen atom, with its lone pair of electrons, is the key to their reactivity, making them highly interactive. Like a cosmic dance, amines engage in various chemical reactions, forming bonds and breaking others, leading to the creation of countless compounds with diverse properties. This dynamic nature makes them indispensable in chemistry. From the simplest amine, methylamine, with its fishy odor, to the complex structures found in life-saving drugs, the world of amines is full of fascinating discoveries and endless possibilities. So fasten your seatbelts as we embark on an exciting journey to explore the amazing world of amines, where every molecule has a story to tell. Amines are like families, with different members having varying levels of substitution. Just as each family member has a unique role, each type of amine has distinct characteristics based on its structure. We classify them based on how many alkyl or aryl groups are attached to the nitrogen atom. This classification helps us understand their behavior and reactivity. Primary amines, like the responsible older sibling, have one alkyl or aryl group. They are the simplest form of amines and often serve as the building blocks for more complex structures. Secondary amines, like the playful middle child, have two. These amines are more complex and exhibit different properties compared to primary amines. And tertiary amines, like the free-spirited youngest, have three. Their increased substitution makes them even more unique in their chemical behavior. Think of a simple amine like methylamine, CH3NH2. This primary amine has just one methyl group attached to the nitrogen, making it straightforward and easy to understand. Now picture dimethylamine CH3-2NH. It's a secondary amine with two methyl groups flanking the nitrogen. This added complexity changes its properties significantly. Finally, envision trimethylamine CH3-3N. This tertiary amine has three methyl groups surrounding the nitrogen, like planets orbiting a star. The increased substitution level makes it quite distinct. This tertiary amine has three methyl groups surrounding the nitrogen, like planets orbiting a star. But wait, there's more. Amines can also be simple or mixed. Amines can also be simple or mixed. Simple amines have identical groups, while mixed amines have different groups attached to the nitrogen. In simple amines, all the alkyl or aryl groups are the same, like in our methylamine examples. This uniformity makes them easier to study and predict. Mixed amines, on the other hand, have different alkyl or aryl groups attached to the nitrogen, adding another layer of complexity to their molecular structure. This diversity can lead to a wide range of chemical behaviors and applications. Understanding the classification of amines is crucial for predicting their properties and reactivity. This knowledge is essential for chemists and researchers working with these compounds. It's like knowing the players in a cosmic game of chemical interactions. Each type of amine plays a specific role in the grand scheme of chemistry. With this knowledge, we can begin to unravel the secrets of how amines shape our world. From pharmaceuticals to industrial applications, amines are everywhere, influencing countless aspects of our daily lives. Naming amines is like giving them a cosmic address in the vast universe of organic chemistry. We use two main systems, common names and the IUPAC system. Common names are like nicknames, often based on the alkyl groups attached to the nitrogen. For example, CH3CH2NH2 is called ethylamine, combining the ethyl group with amine. The IUPAC system, on the other hand, is more systematic, like a universal language for chemists. Here we treat amines as alkanamines, replacing the EE in the corresponding alkane name with amine. So, CH3NH2 becomes methanamine, and CH3CH2NH2 becomes ethanamine. For more complex amines, we number the longest carbon chain containing the amino group and indicate the position of the substituents. For instance, CH3CH2CHNH2CH3, with the amino group on the second carbon of a 4-carbon chain, is named butan-2-amine. If additional alkyl groups are present, we list them alphabetically, along with their position on the main chain. Mastering amine nomenclature is essential for communicating effectively in the world of chemistry. It's like learning the constellations in the night sky, enabling us to navigate the vast universe of organic compounds. Section 4. Preparation of amines reduction methods. Amines, like stars forming from cosmic dust, can be synthesized through various methods. One common approach is reduction, a chemical process of adding electrons. Imagine it as giving a boost of energy to a molecule, transforming it into an amine. One method involves reducing nitro compounds, molecules containing the NO2 group. By introducing hydrogen gas, H2, and a catalyst like palladium, Pd, or platinum, Pt, we can break the nitrogen-oxygen bonds and replace them with nitrogen-hydrogen bonds, yielding the desired amine. Another technique is reducing nitriles, compounds with the CN group. Here we employ a powerful reducing agent like lithium aluminum hydride, LiAlH4, to add hydrogen atoms to the carbon and nitrogen of the nitrile group, forming a primary amine. These reduction methods are like cosmic recipes for creating amines, providing chemists with powerful tools to synthesize these versatile compounds. Each method has its advantages and limitations, and choosing the right one depends on the specific amine we want to create. Section 5. Preparation of amines ammonolysis and Gabriel synthesis. Amines can also be prepared through other ingenious methods, like assembling a complex molecule from smaller building blocks. One such method is ammonolysis, where we react an alkyl halide with ammonia, NH3. Imagine it as a molecular dance, where the halogen atom in the alkyl halide gets replaced by an amino group, forming a new amine. Another fascinating route is the Gabriel synthesis, named after its discoverer, Sigmund Gabriel. This elegant method specifically targets primary amines, using a clever protecting group strategy. We start with phthalimide, a cyclic compound which reacts with potassium hydroxide, KOH, to form potassium phthalimide. This intermediate then reacts with an alkyl halide, replacing the halogen atom with the phthalimide group. Finally, we cleave the phthalimide group using hydrazine, N2H4, revealing the desired primary amine. The Gabriel synthesis, like a carefully choreographed ballet of chemical reactions, highlights the ingenuity of chemists in their pursuit of synthesizing complex molecules. These methods, along with reduction techniques, provide a diverse toolkit for creating amines, enabling the development of new materials and technologies. Section 6. Physical properties of amines. Amines, like celestial objects with unique characteristics, exhibit a range of physical properties that influence their behavior. These properties are essential in understanding how amines interact with their environment and other substances. Their state at room temperature, for instance, depends on their molecular size and structure. Smaller molecules tend to be gases, while larger ones can be liquids or solids. Smaller amines like methylamine and ethylamine are gases with a characteristic fishy odor. This odor is often used as a quick identifier in laboratory settings. As the carbon chain grows, amines transition to liquids and eventually solids, with their volatility decreasing. This change in state is due to the increasing molecular weight and stronger intermolecular forces. Solubility is another crucial property that determines how amines interact with solvents. Lower aliphatic amines, with their ability to form hydrogen bonds with water molecules, are soluble in water. This solubility is vital for their use in various chemical reactions and processes. However, as the hydrocarbon portion of the amine increases, the solubility decreases. This is because the non-polar hydrocarbon chain resists interaction with polar water molecules. Amines are also soluble in organic solvents like ether, benzene, and alcohol. This property is useful in organic synthesis and extraction processes. Boiling points of amines are influenced by intermolecular forces. These forces determine how much energy is required to change the state from liquid to gas. Primary and secondary amines, with their nitrogen-hydrogen bonds, can engage in hydrogen bonding, leading to higher boiling points compared to alkanes of similar molecular weight. This makes them more stable at higher temperatures. Tertiary amines lacking NH bonds cannot form hydrogen bonds amongst themselves and therefore have lower boiling points. This makes them more volatile and easier to evaporate. Understanding the physical properties of amines is crucial for predicting their behavior in different environments. This knowledge helps chemists design better experiments and develop new applications. It's like knowing the climate and terrain of a planet, allowing us to anticipate how life might adapt and thrive. Similarly, understanding amines' properties helps us predict their reactions and uses in various fields.